Now the equation is I equals to C dv dt. Okay. Now if I write it in a different way, how it will look like? If I write it in a different way, how it will look like? Okay. So V T will be 1 by C integration I dt. Now let's say from t0 time to t1 time, we are considering this particular time frame, and at t0 time the initial voltage stored in the capacitance is VT0. Then the final voltage VT1 will be 1 by C integration t01 to t1 I dt plus the initial voltage, or you can write VT1 minus VT0 equals to 1 by C integration t0 to t1 I dt. Now if I plot this particular equation, okay, if I plot this particular equation with respect to graph, how it looks like. Now let's say I am plotting this one. I will be plotting this equation. Okay. So if I plot this equation, this is, let's say, the current with respect to time, and this is voltage with respect to time. So at t0 and at t1, we are considering that at t0 the voltage is VT0, and let's say it is increasing like this way, and at t1 VT1. Okay. So this is the increase in the voltage. Now similarly with respect to that time, if I plot the current, let's say at t0 the current is I0, and at t1 the current is I1. Then what is this? What is this integration? What is this integration? What is this integration? This integration nothing but the area below this particular curve. Okay. And so VT1 minus VT0 is nothing but this particular area divided by C. This is the equation. Okay. Now we will be talking about inductor. First of all, we would have to understand, or we have to see that how a inductor symbol looks like. Okay. So if I draw a symbol of the inductor, it looks like this. One second. First, let me select the pen here. The inductor look like this. This is the inductor. Now say the voltage across the inductor is V, and the positive direction of the current with respect to the passive sign convention will be like this. Okay. Now because of this particular current, there will be flux linkage. There will be flux linkage in this particular coil, and that flux linkage is denoted with phi. Now the voltage across this particular inductor V is nothing but d phi by dt, that is change in flux linkage, and phi, which is equivalent, or which is proportional to I, that is the current. or you can say phi equals to L into I, and this is the inductance of the circuit. Now this inductance phi equals to L into I, or V equals to d phi dt, or we can say V L into di dt. Okay, now let us see how this inductor, or we can say that the equation, the graphical representation of the inductor. So if I modify this particular equation, similar whatever we have done in case of capacitor, then what we can get? We can get is I t is equals to 1 by L integration Vt. Now we are very much concerned from time t0 to t1. So at time t1, the current through the inductor is IT1, and the equation or integration is from t0 to t1 Vt plus the initial current at time of t0. Okay, now we will be getting IT1 minus IT0, which is 1 by L integration t0 to t1 Vt. Okay, remember this particular equation. Now if with respect to this equation, if we draw the voltage and current curve with respect to time, how it looks like. Okay, now this is the current, and the direction we are plotting t, and here we will be plotting V versus t. So let's say at t0 initial current is IT1, and the current is increasing like this up to t1. Okay, so here the value is I t0, here the value is I t1. Okay, now if I plot it here, then the voltage say is getting increased like this way. It is Vt0, here is Vt1, sorry, here it is Dt. So this area under this curve, it is nothing but integration t0 to t1 Vt dt, and this value change, that is I t1 minus I t0 will be equals to that area, this area divided by L. Okay,